Alrighty. So let's do this. Alrighty. Go away. Alrighty, so I am back. We can get rid of this guy. So last time we finished by doing an example of kind of a multi-unit dimensional analysis. We're going to continue more dimensional analysis today. I want to start off by doing something that has units that are either squared or cubed. So, for example, the units for area might be something like centimeter squared, meter squared, kilometer squared, something like that. We can go ahead and work with that. So let's say we had something that was, 3.68 square meters. And if we wanted to, we could find out how many square centimeters that's going to be. We remember that we have our conversion factor that we were able to get from that chart, right? We know that 10 to the negative 2 meters is 1 centimeter. So we can go ahead and use that. If we do, as always, we're going to put the unit we want to cancel out on the opposite side, so in this case it's on the denominator. And so we can go ahead and do that. Good morning. And if you look, we have now 3.68 times 10 to the negative 2 centimeters times meters. I don't like that unit. That's kind of awful, right? If we think about it, meters squared divided by meters, we'll still end up with 1 meter left over. Meter unit, that is. So let's see, time to close the door so Oz's barking is not as obvious to us. So that's not a good thing. We have not finished our task here. However, if we see that we had this number here, the 3.68 times 10 to the negative 2 centimeters times meters, we could go ahead and use our conversion factor again, right? And by doing this, now, there we go. Now all of our meters have finally canceled out. And we know centimeters times centimeters should be centimeters squared, right? That's how the unit multiplication works. And so doing this, we're able to get the answer that we're looking for. So we're able to solve for how many square centimeters that's going to be. All right, so if we look at this, we had square units, and that meant we had to do our unit conversion twice, right? And that kind of makes sense, right? Square units means you have 2 of that unit, right, already incorporated into your number, your measured quantity. And in this case, we had to use the conversion factor twice because it was squared. What we could have done also was just square the conversion factor. So we remember that 1 centimeter was 10 to the negative 2 meters. If we square the whole thing, that tells us 1 centimeter times 1 centimeter is just 1 centimeter squared, right? Let me make that a little arrow. And remember, when you are going to be raising exponents to an exponent, you multiply them together, right? So we should end up with 10 to the negative 4 meters squared. And if we go ahead and use that, 3.68 meters squared times 1 centimeter squared over Oh, did I do this wrong, guys? Why did nobody tell me? Yeah. This should be positive 4 over here. Right? Because negative exponent on the bottom means it comes up to the top as positive. You gotta keep me on my toes. And so by doing this, we'll get our answer in just one step. Because we can see already that meters squared cancels with meters squared. And we'll be left with centimeters squared right away. Alrighty, so hopefully nothing too crazy there. If we have something that's cubed, guess what? Same idea, right? Let's say we had, I don't know, how about 208 cubic inches, and we wanted to see what this was in cubic feet. So we have our conversion factor. We know that 12 inches is 1 foot. And so if we have cubic units, again, we're going to have the same thing. We could do it 2 different ways. We could do this 3 times. So just like before with the squared ones, we had to do it twice. This time we're going to do it 3 times. My hand is going to fall off from writing all of this stuff. And finally, we'll be able to see, okay, 1, 2, 3 of the inch units will cancel out cubic inches. And we'll see that feet times feet times feet is cubic feet. That's good. Doing the math, let's see. What was it, 208? Yeah, 208 divided by 12 divided by 12 divided by 12 is going to be 0.12037, whatever, feet cubed. Apply our sig figs, and we're going to end up with 3 sig figs here, so 0.120 cubic feet. Okay, or if we wanted to save space, we could just do it all at once by cubing our conversion factor. So 12 inches is 1 foot. Cube the whole thing. That means that 1728 cubic inches is 1 cubic foot. Right? That's just 12 times 12 times 12. Inches times inches times inches is equal to 1 times 1 times 1 times feet times feet times feet. So that is going to be our conversion factor. If we go ahead and do it right away, we could just plug this 1728 cubic inches in, and that'll give us our answer right away. So I prefer kind of doing it the second way, where we just kind of make the conversion factor into what we need it to be, just for purposes of space. Like, nobody wants to write this stuff out 3 times. And like, could you imagine if instead I asked for like yards or something instead of feet? You'd have to do it another, bunch of times, or it could get messy. So I think it's easier to just go ahead and cube your conversion factor or square it, depending on what you're looking to do. All right, does anybody have any questions on those 2 before we do another, perhaps more challenging example? Alrighty, not seeing anything. So of course, as always, if something comes up, just go ahead and write it out, and we'll address it. So let's see. Let's make up something fun here. So let's see. Let's go to physics. We can talk about acceleration. Meters per second squared. Yeah, we can. Yeah, let's do this. Okay, so let's say we know we have gravity is 9.8 meters per second squared, right? That's the acceleration due to gravity. Let's see. I want that in... Let's make this pretty complicated. I want this in feet per square hour. Or you know what? Let's make it worse. We'll do inches per square hour. Why not? All right, and I'll go ahead and give us our conversion factors. So we remember maybe from last time that we had 3.27 feet as 1 meter. We remember from just a moment ago 12 inches in a foot. 60 seconds is 1 minute, and 60 minutes is 1 hour. Sorry, Paulette, I know that seems to be a pretty common thing. It's possible that the internet connection you have at home is just not great. It's possible maybe like you have other people also using it at the same time, so it could be like some interference there. But again, sorry, nothing I can do about that. So it may just be better to just watch the videos once I can put them on YouTube, or just maybe afterwards. Okay, so with these, we can go ahead and kind of plan out what we want to do. So remember, when you have kind of more than one step involved, it's a very good idea to plan it out first. So we know we could start on the top or the bottom, does not matter. I usually like to do it from the top. So if we look at our conversion factors here that we're given, we have one that will give us from meters to feet. And we can go from feet to inches. And so that'll give us the numerator unit correctly. And then we're going to have to start working with the denominator. And so we do have a conversion between seconds and then minutes to hours. So if we look, we're going to have to do four steps. However, it's important to note that these ones on the bottom here that I've put little stars on, you know what, let me put those on top just so it's not like I'm multiplying them. These two steps are involving square units changing. So we should probably go ahead and square our conversion factors that we would use in that step. Let's just do that right away. So we're going to now have 3,600 seconds squared equals 1 minute squared, and then 3,600 minutes squared equals 1 hour squared. Okay, so we'll want to go ahead and prepare our conversion factors in advance here. Okay, so we had 9.8 meters per second squared. Our first conversion, we're going from meters to feet, so we'll use the meters to feet conversion, this one up here. Looks like we are given meters, so let's put that on the bottom to cancel it out. So we'll have 3.27 feet on top. Since we know we have four conversions to do, we can go ahead and put that. Next, we see that we have feet to inches. So far so good. We have that conversion factor. And now we're going to start using these two down here. Because we're now going, if we look at our units kind of where we are so far, meters have canceled, feet have canceled. We're now on inches per second squared. That's where we want to be. That was right here, this kind of like middle step. And so now we're going to go ahead and put in our square stuff. So we have seconds on the bottom, seconds squared on the bottom. So we're going to go ahead and move seconds squared on top. And as always, we're going to carry along the numbers that come with it in our conversion factor. And we're going to do the same thing for minutes to square minutes to square hours. And so let's just go ahead and double check our units. So we have seconds squared on the bottom, seconds squared on the top. Those cancel. minutes squared on the bottom, minutes squared on the top, those cancel. So we end up with inches per hour squared. That's what we were looking for. And it looks like we have a lot of math to do here, so let's go ahead and do it. So we have 9.8 times 3.27 times 12 times 3600 times 3600. And we get this crazy big number. I'm going to just write it down here because I will not have space otherwise. Oh no, it's 3793920. Right, inches per hour squared. All right, some completely absurdly big number. Let's consider sig figs, as always. Of course, we have our given number here. This one had 2 sig figs. And if we look at our conversion factors, there's only one that is going to be going between metric and US. The rest of them are all within the same system, so we can ignore them. However, this 3.27 feet thing does have sig figs, so we have to worry about sig figs in these 2 spots. And so that tells us that we're going to need 2 sig figs at the end. So, let's see, let's do blue. We have to round here. Oh my goodness. Okay, so we need to have 50, 1, 2, 3, 4, 5, 6, 7, 8. But this number would only have 1 sig fig, right, as it is written. So let's throw this in scientific notation so that we can make sure that it has 2 sig figs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this number would be 5.0 times 10 to the 9 inches per hour squared. And so that would be our kind of final number here. So if for whatever reason we needed to convert this from meters per square second into inches per square hour, that's how we would do it. And so notice we did have some square units involved here. It just depends what you're given, right? So sometimes you will need to square or cube your units depending. There is one thing that you may get confused with this. There is one conversion factor that is important for us. It's 1,000 liters is 1 cubic meter. This already has cubic meters in it, okay? So if you're going to use this conversion factor in a problem, you don't need to mess with it anymore. It's already got the cubic part as already incorporated. This is the same thing, by the way, as saying 1 ml equals 1 cubic centimeter. So these are the same conversion factor. If you are ever using these, you do not need to cube them anymore or square them or anything like that. If you were to square one of these or cube it, you could get like 1 ml squared is 1 cm to the 6th or something. And these units just don't make sense to us. Like, these are already volumetric units, so it's like 6 dimensions doesn't really make sense. It'd be like, what the heck? Why are we doing that? Okay, so you shouldn't need to ever do that. Okay. Any questions so far? My allergies are killing me today, by the way. Sucks, but oh well. We'll live. Okay. Then moving on, there's one more thing I want to talk about, which is density, which is abbreviated with the Greek letter rho, not a P. Unfortunately, it's not a D either. Like, that would make too much sense. This is a conversion factor between mass and volume. typically, the units of mass that we're going to deal with are grams or kilograms, and then volume we either would use like meters cubed or milliliters or something like that. Those are pretty common units that we would use here. So this is just a conversion factor. It's a way of saying, okay, let's say I've got something that weighs 30 grams. And let's say it was 11.9 milliliters. So this conversion factor is going to be able to convert units of mass into units of volume. Typically, when you're doing a unit conversion, you're staying the same thing. Like a unit of distance would stay a unit of distance. Like, for example, we had, in this example, we had a distance unit and a time unit. We ended up with a distance unit and a time unit at the very end. But density is going to be a special one that can convert between different quantities. So what we could do is just algebraically solve for this. We could see that the density is going to be 11.9 milliliters per 30 grams. And look, we've already got our conversion factor. So this is telling us that we're able to now take this information and use it for other problems or something, or we could just solve for it. No problem there. So technically this unit would be like something like this. Like if we were to go ahead and do the math here, typically it's presented as the opposite way around. Remember, conversion factors you could put as fractions either way, one over the other or the opposite way. Typically, density is presented as grams over mLs. So typically you're solving for it this way, but you could totally do it the other way around. You could have it instead be whatever point something mLs divided by 1 gram. Totally okay as well. This is telling us that 1 ml equals 2.59 grams. That's a conversion factor. And again, we could have done it the other way around where we make the grams have 1 instead. We could say also, let me just do the math for here. We could say that 0.386 ml equals 1 gram. We could do either way. It's the same thing. So it's just a conversion factor. Anytime that you are going to be converting between mass and volume, you're going to be using this as a conversion factor. A lot of things that, for whatever reason, people like to use the formula, the mass divided by the volume, but it's just like unnecessary. You could use that if you really wanted to, to solve for the density, but I don't want you guys to just memorize kind of pointless formulas. It's not really necessary, especially when you can just get the units from your conversion as it is. Okay, so let's do an example with it. So let's say we have 10 mils of ethanol, and the density of ethanol is 0.789 grams per ml. So this conversion factor tells us 0.789 grams equals 1 ml. That's what the density is telling us. They're equal to each other. So depending on what we want to do, we would put one on the top, one on the bottom. So if we have 10 ml to start, we're going to want to put ml on the bottom, right? We want the units to cancel out. And so we would put 0.789 grams on top. We would do the math. Thankfully, this is not too bad. I could do it in my head. So 7.89 grams would be our answer here. So it's just like any other conversion factor. we're going to use it to convert between two different quantities here. So say maybe now we have let's see, I don't know, 22.6 grams of ethanol. We could see what the volume is going to be by using the same idea. 22.6 grams. If we look here, we can say, okay, grams has to go on the bottom. Mils has to go on top. And let me see here. Let's do the math. 22.6 divided by 0.789 will give us 28.6 mLs. Okay, so density you can use whichever way you want. In this case, we put grams on top for the first example, and then we put grams on the bottom for the second example. It just depends what you're going for, which units you're starting with, and what unit you want to end up with. Okay, no different. If you wanted to, again, you could use a formula to solve these. If we started with that 10 mLs, you would just plug that in for the volume if you want to do rho equals m over v and just solve for m. Or you could do the same thing for the other one, but I think it's just easier to use them as conversion factors. To me, that just makes a lot more sense, and it's going to be a lot easier when you get into the next level of chemistry that's going to have many steps put together involving density as well as other conversions. Okay. So density, just another conversion factor. I encourage you to look at it that way. But if you ever see it, you could use a formula instead. All right. Any questions on that stuff? So again, you do have a worksheet that is on dimensional analysis. That's this stuff here, the unit conversions. So you're going to want to work on that. I will probably post another one depending on how far we get today. Otherwise, I might just post it next week for our next topic. Alrighty, so I'm not seeing any questions in the chat box. You guys are always so sleepy. Come on, it's 9:30. Wake up. And it's our Friday, basically, you know? It's our last day of streaming for this class. So, by the way, you will see me streaming for Chem C101 tomorrow. We're a little bit behind in that class, so I'm going to be doing a little bit of catch-up tomorrow. So you'll see me streaming, you'll get a notification, but that is not for you guys. Okay, so that's for the other class. Okay. So, not seeing any questions, so hooray, we are done with Chapter 2B. So, our next one is Chapter 3A, which we are going to be talking about atoms. Alrighty, so at the beginning of the chapter, it's kind of a history of how we learned about the existence of atoms and how we learned that there were different particles that make them up. So you're welcome to read that on your own. I tend to not focus too much on the history. I think it's cool, but it's not necessary for your understanding. So you've probably learned before that atoms are kind of the smallest unit that we can kind of break something up into. So if we had a piece of copper, copper wire or whatever, it's a pure substance, right? All the atoms are the same. We would basically, if we just keep chopping that copper up, and somehow we were able to just keep chopping it, we would be able to reduce it to a single copper atom. However, we would not very easily be able to break that apart any further. So atoms are kind of the smallest little component, the smallest chunk you can possibly make of a substance. All right, and we know from various experiments in science that atoms are made of a few things. They're made of what are called subatomic particles. And these are going to be the proton, the neutron, and the electron. Alrighty, and we know some properties about these as well. We know that these have a charge on them. They have a mass associated with them, and they have a location within the atom. Location, I can spell. Yeah, there we go. We know that protons are positively charged, and electrons are negatively charged, and neutrons do not have a charge. They are neutral, hence neutron. We also know that protons and neutrons are both approximately 1 atomic mass unit. It's a very small unit, but they're about the same. And an electron is roughly 1/2000 AMU. Yes, proton's positive. So we can see that the proton and neutron are roughly similar in mass, but the electron is much, much smaller. So we're going to see when we're looking at the mass of an atom, we mostly just focus on the protons and neutrons because the electrons are just since they're so much smaller, they're going to be like negligible towards the entire mass of the atom. We also know that the protons and neutrons are located in one little tiny part of the atom, which is called the nucleus. It's kind of right in the middle. And that's where all those protons and neutrons are kind of hanging out. And the electrons, if I can spell correctly, are kind of orbiting the nucleus. So a simple model that you've probably seen before, you have your nucleus in the middle, and you have some orbit, for example, and you've got some electrons just whizzing around in there. Those are going to be your electrons. And all your protons and neutrons are in that one little dot. If we were to give you kind of a size comparison, like consider that the nucleus consider it like a grain of sand. Whereas the entire atom, including where the electrons are orbiting around, is the size of a baseball stadium. So consider, for example, a grain of sand on the pitcher's mound or something, kind of like right in the middle. Yeah, exactly. And those electrons are going to be, basically, they can occupy a bunch of different spaces throughout that entire baseball stadium. So the nucleus is kind of that one grain of sand, and it kind of stays in the middle. But the electrons are able to go from any of the different seats within your baseball stadium, where they're on the bases or they're in the outfield or something. So just consider like the size difference here. So grain of sand versus a baseball stadium. Okay, huge difference in the nucleus size versus the entire atom size. So those electrons can go all over the place, wherever they want to go. They're just zipping around like crazy. All right. What's interesting to note is that almost all of the mass of the atom is in that nucleus. So, it's just, everything is all right there on that grain of sand. And most of the atom, that baseball stadium, is just empty space. And so, you think about it, we're mostly, empty space. So the difference here is about 10 to the 15 or so in terms of the size differences. So that's, a quintillion or something. So if you think about, your body, 1/quintillionth of that is actual mass, and the rest of it is just empty space. So 10 to the 15th of your body is empty space, and you just have small amount of mass everywhere. It's pretty mind-boggling. And that's why we have to fill the void with, like donuts and various substances that make us happy. So, yeah, fun stuff. Okay, cool, cool, cool. So, with regard to those, we talk about these protons and neutrons and electrons in different ways. So, I'm going to describe to you how we very often talk about different atoms. So, with this, we use what's called AZE notation sometimes, where A is the mass number, which is the number of protons plus the number of neutrons. Z is going to be the atomic number, which is the number of protons. Alrighty, and then while it's not written here, often we have a charge associated with a particular atom. And we're going to see how to calculate that charge in a little bit. Okay, and the last thing that we're going to have here, this E, is going to be the element symbol. So let's see, do I have a periodic table floating around here? Let's see. Does this have one? Yeah, okay, cool. So, periodic table, here it is. You're going to see that all of these elements, the 118 elements on here, all have symbols associated with them. So those are the letters that are on their names. For example, we have Na for sodium, or S for sulfur, or whatever it happens to be. It'll either be a single capital letter or a capital letter and a lowercase letter. All right, so kind of from this point on in class, I would recommend that you just find a periodic table online that you like, or when on your phone. There's plenty of apps that just have periodic tables, and you can you're gonna want to use it as a reference. And so we'll talk about that. So let me see. On my phone, I have an app for this. No, I don't. I lied. I deleted it. No, it's right here. Periodic table. Woohoo. So this happy periodic table on my phone, I can click an atom and I can see all sorts of fun stuff about it. So for example, we can see lithium here. And it's telling me that, this is kind of really crappy. It's really small for us. So let me bust out our thing again. Okay, here we go. If we look at lithium on the periodic table, it's right here. We see on top of it is this number 3. I'm sorry, I don't know how blurry this is. I don't know how well my camera will focus. But look on a periodic table. Look just below hydrogen. It's in the top left corner. We're going to see that lithium will have an atomic number of 3. That's what that number on top meant. So this number we got from the periodic table. So that's going to be the number. You're going to see that the periodic table is organized by these atomic numbers. Hydrogen has 1, helium is 2, then lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, etc. They're organized by these atomic numbers. So those are going to be the numbers on the top there, and they're going to follow that. This one, the mass number, I could say maybe this one is 6 or something. This one would be given to you. Okay, nowhere on the periodic table for lithium are you going to see a 6, and we'll explain that next week, why we don't see a 6 there. And let's say that this lithium is neutral, so there's no charge. Typically, if it's no charge, we could write a 0 there. It's just called periodic table. And it has enough information. There's probably like 500 different periodic table apps. You just want one that has the basic numbers and symbols and names and everything. So that'll be nice for you to have. Okay, so if we go ahead and look at this, we can try and figure out how many protons, how many neutrons, and how many electrons this particular lithium atom has. So if we go back to what this AZE notation meant, we can see the atomic number is kind of our easiest one to go to. That one just tells us the number of protons right away. So if we look at this particular representation of lithium, there's a 3 on the bottom. That tells us there are 3 protons. The next one we can look up is we see this mass number, which is protons and neutrons. So that tells us that 6 equals the protons plus the neutrons. Since we already know that the protons were 3, that tells us that we have 3 neutrons. Right? So that number at the top there was protons and neutrons, so we're able to figure out how many neutrons we have. And so, if the atom is overall neutral, which means no charge. Yeah, exactly. So if there is no charge, that means that you have an equal number of positives as well as negatives. So we're going to see that because there's no charge, we have the same number of protons as we have electrons. So charge is going to be the number of protons minus the number of electrons. And so if our charge was 0, and we know we had 3 protons, then we're obviously going to see that the number of electrons is 3. Right? Since that has to be 0. Okay, so far so good, hopefully. Let's go ahead and do quite a few more examples. So let's do these, yeah. Okay. Yeah, that math is easy, right? We can do this math. And we can look at the number of protons, number of neutrons, number of electrons here. Okay, so let's go ahead and do it. We can see number of protons again is going to be our easiest one to figure out. We can see that all of these will have 12. We know that just because that's the bottom number in all of them. Let me do this in blue just to make it exciting and fun. These all have 12, right? We get that because that's the atomic number. We could see that on the periodic table, or we just see it's the 12 on the bottom there. So if we go on to neutrons, we remember the mass number, the one on top, is protons plus neutrons. Yeah, it's not complicated compared to the math we did earlier, right? For sure. So this one is going to be 24 minus 12. So that'll be 12. This one will be 25 minus 12. So that's 13. And this will be 26 minus 12, which is 14. So it looks like we have different numbers of neutrons in these guys, which is totally okay. And we see that all of these are not charged. Typically, we don't write 0. Hold on, Gumbo's wanting to leave. Okay, Gumbo, go on. You want to go out? Go on. Or do you want to stay now? What do you want, dude? Go on. Okay, you want to stay? Okay, then let's go say hi to everyone. Okay. Yes, very good. Okay, so Gumbo does not want to leave after all. And since these are all uncharged, we know that the electrons are going to be the same as the protons. Alrighty, so I have a handy-dandy vocab lesson for us here. These are called isotopes. They are the same atom, but different number of neutrons. Or another way to say this would be a different mass number. And instead of atom, I'm going to write element actually, because technically they're different atoms. Alrighty, so these three particular atoms are isotopes of each other. They're all magnesium atoms, however, they have different numbers of neutrons. Okay, and so we see in this example, one of them had 12, one had 13, one had 14, and these are what we are going to call isotopes of each other. Alrighty, and how we would talk about these is typically, you could say something like this. This is might be how you'd write it. And you'd be referring to one particular isotope, the one that has a mass number of 26, and you would read this as magnesium 26. Like, that's how you would read it aloud. Sometimes you'll also just see it written like this, without writing the 12 on the bottom. Same thing, you would read it the same way. So when you hear people talking about magnesium 26, you know they're talking about this particular isotope. You've probably heard, people talking about uranium 235. That's an isotope of uranium. Or uranium 238, same thing, it's a different isotope of uranium. Okay, so those are isotopes. They have different number of neutrons. Alrighty, and so let's do another couple examples. Okay, let's do these ones. These three. So, protons, neutrons, electrons, let's figure them out. So, if we look at these, again, protons should be super easy for us. Exciting. Remember, we're just copying the bottom number there, nothing particularly new. Neutrons, we're going to subtract the two numbers, so top number minus bottom number. And for these, it's going to all be 12. Alrighty, and then if we look at the electrons, because again, none of these are charged, we're going to see that they have the same number of electrons as protons. And so, we see that these are different elements, right? One is sodium, one's magnesium, one's aluminum, right? They're three different elements. They have different symbols, so they're different elements, right? So that for right now, based on this particular chart, we can see, okay, so different number of protons or electrons means different element. And we are actually going to come back in a moment and make this a little bit more specific. But let's do another one first. Let's do this one. So notice I've written in charges this time. In chemistry, we typically write the number before the charge. That's just standard. So when you see on that aluminum there, it says 3+. That means it's got an overall charge of +3. So protons, neutrons, electrons. Again, proton's easiest one to do. It's already there for us. I haven't changed the mass numbers, so they're still going to just all be 12. And now we have to look at the electrons. So we have a positive charge on that sodium. So we know that charge was proton minus electron, right? Yes, we are going to get the vocab on those. So we have a charge of +1 equals 11 protons minus electrons. And so therefore, electrons is 10 in this case. And if you do the math, we're going to see that all of these guys have 10 electrons. And so looking at this now, I'm going to tell you these are called what are called ions. So ions just means charged. All right, and we have special names. Positive ions are going to be called cations, and negative ions are called anions. So just vocabulary there. And if we look at these, we're going to see that the number of protons was changing, but not the number of electrons in this particular case. However, they're also all different elements. So that tells us even though these guys all had 10 electrons, same number of electrons, they're still different elements. And so we're going to actually define elements as just the number of protons. So every single sodium atom will have 11 protons. Okay, it does not matter how many electrons or how many neutrons it has. Sodium is defined as having 11 protons. All right. If we were to just kind of summarize this thing, if we change the number of protons, that means we have different elements. If we change the number of neutrons, those are going to be different isotopes. And if we change the number of electrons, those are going to make things different charges. And then if it's charged, we call it an ion. Okay, so we're going to have all this vocabulary here for understanding how to compare these things. So, yeah, we can do a couple examples. We have 5 more minutes. We can say, let's just come up with a couple of things here. So let me tell you that I have a phosphorus atom that has a mass number of 32 and it's got 18 electrons. Okay, so this is what I'm giving you. So I want us, Maya, let me see. I think I put it in Discord somewhere. I'll show you in a sec. But let's do this problem. So looking at this, I've given you kind of half of the picture here. However, this Sherry, the tutoring thing is a kind of, you just tell them you need tutoring and they'll assign someone to you. I'll show you that in just a second. But we'll just do this problem first and then we'll go to Discord. So I've given you an incomplete picture here, but there's enough information that you'll be able to solve for the rest of them. So you will be able to figure out the protons and neutrons, as well as everything else that's missing. So we are missing two components here from our symbol, right? So there are four things that we are missing here. So anybody have any idea how to get one of these numbers? Any idea whatsoever? I'll give you a hint. It's the thing that I can't show you because it's too blurry. Or you can look at it on your phone, on an app, or you can just Google a particular picture of it. Yeah. Periodic table. So if we look at our periodic table, we're going to want to find phosphorus. It's right over here. And that tells us, I know you guys can't see it, but there's a big old 15 on top of it. Okay, so we're going to go ahead and understand that the number here for that particular one is 15. That's the number on the periodic table that tells us we have 15 protons, right? So periodic table will always tell you the name or number of protons for a particular element. Okay, so you say 16 protons, but if it were 16 protons, it would actually be sulfur. Number of electrons I already gave you. I already gave you 18 electrons. We'll work through this, I think, and then we'll be continuing this on next week. So number of protons, 15. We got that from the periodic table. And remember, that's the number that's going to go on the bottom there. Okay, so number of neutrons then. Do we remember how to solve that? That one is going to be the top number minus the bottom number, right? So the mass number subtracting by the protons. Yeah, you're going to get 17 neutrons there. So that was 32 minus 15 is going to be 17. So that number is going to go here. And now the part that we're missing, we are missing the charge of this particular thing here. And so we remember that charge is proton minus electron. So we'll just say X is 15 minus 18, which is going to be -3. Right, and so we would then put, oh my goodness, go away. 3 minus up in the top. So it's actually 8, yeah, exactly, yeah, good. So we have now completed this particular symbol, and we've figured out the rest of the numbers that we needed to plug in here. So I want to show you guys the tutoring thing before I head off for the day for you guys. So let me swap this over to Discord real quick. I believe that's window 2. Is it window 2? Yes, it is. Okay. So where are we here? I think I put it here. Yeah. Okay. So if you go to the helpful info thing up on the very top here, there's this link that will you can click here to request a tutor. I'm not quite sure what's going to happen, but there's apparently a box that you check for online, because of course during COVID they're not going to do in-person tutoring. So there's like a form you fill out, and just make sure you check the online box, and they will contact you with like information about the tutoring. And this is completely free, provided by the college. Okay, and Khan Academy or YouTube will always be your friends for this stuff. So okay, so that's where we're gonna find tutoring if you need it. Okay, so I'm gonna go ahead and I think I will give you one more worksheet, just because you guys love homework so much. So I'll put that up in a little bit later today. Yeah, so it looks like Paulette has already done this. So check your school email after after you sign up, and they'll probably give you more information. Okay. So with that, I will see you guys next week. So have fun doing your homework. Don't forget they are going to be due on Sunday night. So 11:59 midnight, or just about midnight. So don't forget to do that. And you know what? Just because it is Wednesday, um, I will post something in Discord that I want you guys to just write something about. So it's going to be, like how last week it was kind of introduce yourself and ask me questions and stuff. It'll be something like that where it takes like 2 minutes to do, but just something to keep us, participating and engaging with each other. So, okay. With that, I'll see you guys next week. So stay safe. Don't forget, Monday is actually Labor Day, so I will see you on Tuesday. Okay, so enjoy your Labor Day weekend as best you can. I know that none of us can actually go out and do anything. Oh, by the way, look at that. They're together, squashed into one bed. That's cute. Okay. Yeah, have fun. Okay, see you guys.